Hello, we are Team 4, and today we'll be discussing the optimization of a vertical farming system. Vertical farming maximizes space use efficiency by stacking crop growth, therefore allowing for more crops to be produced within a constrained space. The need for vertical farming is becoming more prominent, especially in cities where space is an expensive commodity. While maximizing the use of space, vertical farming also requires more energy to pump water up to the crops in higher layers, so there are trade-offs between production per area and energy use. The objective function of our system is to minimize the energy per number of crops produced and water usage per area. Our system will grow romaine lettuce. This is convenient because romaine lettuce has constant requirements for light intensity, water pH, and nutrient needs throughout its entire growth process. Our system will be an isosceles triangle structure that has rows of tubing on each side which hold the lettuce along them. The tubes will be connected on the ends as seen in the right figure. Water will be pumped to the top tube and will then flow along the bottom and throughout the tubing. This nutrient-rich water will be absorbed by the roots of the lettuce, allowing them to grow. The two sides of the structure are independent of each other, and therefore all calculations will correspond to one half of the system, demonstrated by width W. The system has three subsystems, which are crop production, electrical power management, and irrigation management. The inputs to our system are the plants, water flow rate, power to run the air conditioning, power to run the water pumps, and power for the lights. The system will then output the energy cost of the system. The variables shared between subsystem 1 and 2 are the slope of the system structure, the length of the system, and the number of layers of plants. The variables shared between subsystem 2 and 3 are the volumetric flow rate. The variables shared between subsystem 1 and 3 are the total number of crops in the system. Finally, there are no coupled variables. Everything external to the system boundary, such as energy costs and food and safety regulations, are outside the scope of this project.
Subsystems 1's goal is to maximize crops produced while minimizing the space used. Subsystem 2's goal is to minimize the amount of electrical power used. Subsystem 3's goal is to maximize water use efficiency. Here's the list of our assumptions from all three subsystems. A few of these were shared between subsystems 1 and 3, while subsystem 2 had introduced a few of its own. These help make our optimization more feasible and practical. For the system, the design variables include the angle of the base to the ground, the length of the system, the number of layers, the water flow rate, and the water recycle efficiency. Also, the objective function of energy cost is to find the least power required per yield of crop while accounting for the fraction of height over width to incentivize the system to be more vertical, and the fraction of water use over the water total to make the system more efficient.
These are the parameters for subsystem 1. These are the parameters for subsystem 2. These are the parameters for subsystem 3. It's worth noting that these parameters were shared across all of the some of these parameters were shared across all of the subsystems and were combined for the final system. These are the intermediate variables for subsystem 1, and crop yield was the objective function for this subsystem. These are the intermediate variables for subsystem 2, with total power consumption being the objective function. And these are the intermediate variables for subsystem 3, with water absorbed by crop being the objective function. These were the final system's constraints, with us considering the integer number of layers, the total height of the system, the acute angle of triangular structure from the ground, the length of the system, the flow rate of water recycle efficiency, and then the water absorbed by crop.
The system was a constrained integer nonlinear programming problem, and it was solved using the genetic algorithm, since the genetic algorithm can deal with integer constraints. And the modeling steps included combining the design variables from the subsystems, as well as the parameters and the constraints, to make one large problem, which could be solved using the genetic algorithm in MATLAB. There were some trade-offs between objectives and constraints. The objective of maximizing number of crops would be constrained by length and also by height. In the subsystem models, there were some differences to eventually their objective functions became intermediate variables of the total system. Variables that were parameters in the subsystem models were then given values that were linked to the other subsystems. So like flow rate from subsystem 3 was able to be plugged into subsystem 2, and number of crops from subsystem 1 was now able to be plugged into subsystem 3. And because of just using one large genetic algorithm function to solve this system, we did not have to apply any system optimization formulation. Upon running the genetic algorithm for the full system, vertical farming system, we arrived at consistent results for 5 different runs. Each run produced a maximum theta of 80 degrees. It nearly maximized length at around 30 meters, and it maximized number of layers around 5. The flow rate was 33 or so. The water recycle efficiency was about 0.85. And the energy cost was minimized to be right around 2,400 for each trial. Theta being maximized makes sense as that would limit the amount of area that the floor space that the system would take up. Length being maximized makes sense as it allows for more plants to take place. And N maximized also allows for more plants. Q being around 33 liters per day allows for adequate water to be given to the plants while not providing excess water that the plants do not need. The recycle efficiency is around 0.85, which is not quite at its maximum, but it's nearing it, and it's about what's feasible for the system. And the minimum energy cost was found to be about 2,400.
Moving on to constraint sensitivity analysis, we basically adjusted the constraints, relaxing them by 10%, which basically means we lowered the lower bounds by 10% and increased the upper bounds by 10%, essentially increasing the possible solution space. We found that the most sensitive variable was theta, the slope angle of the system. When adjusted by 10%, we saw that the change from the original optimized mean value that we obtained was about negative 80%, while the rest of the variables remained well below a 10% change. Moving on to parameter sensitivity analysis, the parameter we decided to test were the distance between crops, the pump efficiency, and the water required per plant. Each of them are picked from subsystems 1, 2, and 3 respectively. Each of them were adjusted plus or minus 10%, and we found that the most sensitive variable was the pump efficiency, where there was about a movement of almost 12% for the plus to minus 10% movement of the variable, while the rest of the variables remained well below a 5% overall change. In subsystem optimization, we observed that the L and N were maximized to 30.48 meters and 5 layers for subsystem 1, but they got minimized for subsystem 2 to 1.22 meters and 1 layer. Theta was maximized at 80 degrees for both of the subsystems 1 and 2. Q was assumed to be 24 liters a day for subsystem 2, and C was assumed to be 1,710 plants for subsystem 3. However, when put all together in system optimization, we obtained an optimal value for both subsystems 1 and 2. We obtained the optimal value for L and N at 30.4 meters and 5 layers. Theta was still maximized at 80 degrees for the whole system optimization. Q was now optimized for both subsystems 2 and 3 at 33.5 liters a day, and C got optimized for both subsystems 1 and 3 at 1,640 plants. As we observed, theta, N, and L have all reached their optimal values, and potentially incorrect assumptions have been resolved Potentially incorrect assumptions that could have been in the subsystems have been resolved when we considered the entire vertical farm as a whole system optimization.
Moving on to the engineering interpretation, the values obtained from both our initial system optimization and subsequent sensitivity analysis align well within real-world expectations. The results of the sensitivity analysis highlight the importance of theta, the slope angle of the system, as the most influential variable. This finding makes sense as theta directly impacts nearly every component of the system. This is because adjustments to theta necessitate changes to the system's total height, length, number of layers, flow rate, water recycling efficiency, and the amount of water absorbed by the crops. As each of these parameters influences the performance of their respective subsystems, it demonstrates how much of a critical factor theta is in the system's overall behavior. Moving on to future work, for future work and potential improvements, we concluded that incorporating transient conditions such as time-dependent changes in temperature and humidity would lead to more accurate and dynamic system modeling. Additionally, accounting for the greenhouse effect caused by sunlight entering through windows would improve thermal predictions. Instead of using a fixed value for humidity, integrating humidity control systems such as humidifiers, along with their associated net energy costs, would enhance environmental regulation. Finally, optimizing the layout and energy use of the entire warehouse system would contribute to both reducing heating power requirements and improving the overall growing conditions for crops. These enhancements would lead to a more efficient and realistic design for the indoor vertical farming system. Thank you.